Welcome to Cosmos and Dreams. Tonight, we explore the breathtaking journey of stars, born from swirling clouds of dust and gas, living for billions of years, and dying in spectacular bursts of light that seed the cosmos with the very atoms inside you. If the universe is your kind of bedtime story, subscribe before you drift off. Now get comfortable, close your eyes, and let science carry you to sleep. Opening meditation. Close your eyes now. Let the weight of the day begin to soften. Let your shoulders settle, your hands uncurl, your breathing slow to something easy and natural. You have arrived at a place of rest. There is nothing you need to do. Nowhere you need to be. The only journey ahead of you is a gentle one, a long, quiet drift through some of the most beautiful ideas human beings have ever discovered. Tonight, we are going to travel far. We are going to travel to places so distant that light itself takes millions of years to cross them. We are going to watch clouds of gas and dust collapse under the weight of their own gravity, ignite into blazing spheres of fire, burn for billions of years, and then, in moments both catastrophic and sublime, give back everything they ever were to the universe that made them. We are going to follow the life of a star. And as we do, you may notice something quietly remarkable. That the atoms in your body, the calcium in your bones, the iron in your blood, the oxygen filling your lungs right now, were forged inside stars that lived and died long before our sun was even born. You are not separate from this story. You are made of it. So settle in. Breathe slowly. Let the images form gently in your mind. There is no hurry here. The universe has been unfolding for nearly 14 billion years, and it will unfold for billions more. Tonight, we simply observe. We wonder. We drift. Part 1: The darkness before the light, the universe before stars. To understand the birth of stars, we must first sit with the darkness that preceded them. Imagine, if you can, the universe approximately 400,000 years after the Big Bang. This is a strange and unfamiliar place, not empty exactly, but not illuminated either. It is a universe filled with matter, yes, but matter that has not yet organized itself into the brilliant, burning objects we now call stars. The cosmos at this stage is a vast, glowing fog of hydrogen and helium plasma, a hot, dense soup of protons and electrons moving too fast, too energetically, to bind together into neutral atoms. Light cannot travel freely through this fog. It is trapped, scattered constantly in every direction, making the universe opaque, like the inside of a cloud. And then, as the universe expands and cools, something extraordinary happens. The temperature drops to roughly 3000 Kelvin, still enormously hot by any everyday standard, but cool enough for protons and electrons to come together and form the first neutral hydrogen atoms. In an event cosmologists call recombination, though it is not really a recombination at all, since the particles had never been combined before, the universe suddenly becomes transparent. Light is released. It streams freely through space for the first time. That light is still traveling today. We detect it as the cosmic microwave background radiation, a faint, cold glow that bathes the entire sky in microwave wavelengths. When physicists Arno Penzias and Robert Wilson accidentally discovered it in 1965, while working with a large horn antenna in New Jersey, they initially thought they were detecting noise from pigeon droppings inside their telescope. What they were actually hearing was the echo of that first great release of light, an afterglow from the earliest transparent moment of the universe, stretched by nearly 14 billion years of cosmic expansion into a whisper so quiet it took decades just to recognize it for what it was. But back in those early moments after recombination, the universe was not yet doing anything as dramatic as making stars. It was settling, cooling. And within its vast, nearly uniform density, there were tiny fluctuations, regions infinitesimally denser than their surroundings. These were the seeds of everything that would come next. Every galaxy, every star cluster, every solar system, every planet, every living thing, all of it would eventually trace its origins back to those tiny, ancient ripples in the fabric of the early universe. Gravity is a patient force. It does not rush. But it does not relent either. Over millions of years, a span of time that is difficult to truly feel, even in the quiet slowness of a night like this, gravity pulled matter toward those slightly denser regions. Hydrogen and helium gas began to accumulate. Large-scale structures began to form. The very first clouds, sometimes called primordial clouds, began to condense. We have never directly observed the cosmic dark ages. They lie at a distance so vast, and in a time so remote, that even our most powerful telescopes have not yet fully penetrated them. The James Webb Space Telescope, launched on Christmas Day of 2021 and deployed at a gravitational balance point called the second Lagrange point, 1,000,000 miles from Earth, is now peering closer to this ancient boundary than any instrument before it. In its first years of operation, it has revealed galaxies forming with startling speed in the early universe, galaxies that, by the models astronomers had previously built, should not yet exist at such early times. These discoveries are not overturning our understanding of cosmology so much as deepening it, complicating it, making it more interesting than it was before. The first stars, the ones that finally ended the cosmic dark ages, were extraordinary objects. Unlike the stars we see today, they formed from gas that contained almost no elements heavier than helium. There was no carbon, no oxygen, no silicon, no iron, none of the richer chemistry that modern stellar clouds contain. These primordial stars, which astronomers call population 3 stars, are believed to have been dramatically more massive than modern stars, some perhaps hundreds of times the mass of our own Sunday. They burned ferociously bright and hot. They lived for only a few million years, brief even by stellar standards. And when they died, they seeded the universe with heavier elements for the very first time. We have never directly observed a population 3 star. They all died billions of years ago, and the light from their formation lies at the very edge of what our telescopes can see, shifted so far into the infrared by cosmic expansion that only instruments like the James Webb can begin to search for their signatures. But we infer their existence from the chemistry of the universe around us, from the pattern of elements we see in ancient, distant galaxies, from theoretical models of how the first heavy elements must have been created, and from the simple, beautiful logic of stellar evolution. The cosmic dark ages ended with fire. With the first ignition of the first stars, the universe flooded with ultraviolet light so intense that it reionized the hydrogen gas surrounding those early stars, stripping electrons away from the atoms that had so recently combined, in a process called reionization. The universe became luminous again, permanently this time, filled with light from the first stellar fires. And everything that followed, every generation of stars, every world, every ocean, every thought, traces back to that first fragile moment when gravity pulled enough darkness together to make a light. Part 2: The Nursery of Stars, Nebulae and the Collapse of Gas Clouds. If the universe is a story about gravity making order from chaos, then a nebula is one of that story's most beautiful chapters. The word nebula comes from the Latin for cloud or mist. And indeed, nebulae are clouds, vast, billowing structures of gas and dust scattered through the arms of galaxies. Some nebulae are illuminated by nearby stars, glowing in gorgeous shades of red and blue and green as their hydrogen and oxygen absorb starlight and re-emit it as their own softer glow. These are called emission nebulae, and among the most famous of them is the Orion Nebula, visible on a clear night to the unaided eye as a faint smudge in the sword of the constellation Orion. Look more closely through a telescope and that smudge transforms into a breathtaking tapestry of glowing gas, within which young stars are actively being born right now, this very moment, as you rest and breathe and let your thoughts grow quiet. Other nebulae are darker, colder regions where the gas and dust are so thick that they block the light behind them. These dark nebulae, the Horsehead Nebula in Orion is perhaps the most photographed example, are not empty spaces at all. They are star-forming regions in waiting, places where the raw material of new suns is accumulating in the cold and the dark. How does a star begin to form inside one of these clouds? When a region of gas becomes dense enough, gravity begins to win. The cloud starts to contract. As it contracts, it heats up, gravitational potential energy converting to thermal energy as the gas compresses. But for a while, this heat can radiate away into space, carried off by infrared light emitted by the dust mixed into the cloud. This cooling allows the contraction to continue without the pressure rising too rapidly. The cloud does not collapse all at once into a single object. Instead, it fragments, different regions within the cloud reaching critical densities at different times, each one beginning its own collapse. This is why stars tend to form not in isolation but in clusters, open clusters of dozens or hundreds of stars, all born from the same parent cloud within a few million years of each other. The Pleiades star cluster, that lovely collection of blue-white stars visible in winter skies, is one such group, a family of stars born together from a single molecular cloud roughly 100 million years ago, now drifting slowly apart as the gravity of the galaxy gently disperses them. As an individual fragment of cloud collapses, it begins to spin. Any slight rotation present in the original cloud is amplified as the cloud shrinks, the same physical principle that makes a spinning figure skater accelerate when she pulls her arms inward. Angular momentum is conserved, and so the collapsing cloud spins faster and faster, flattening into a disk shape as it does so. At the center of this spinning disk, the densest material accumulates, heated by its compression to temperatures of hundreds of Kelvin, then thousands, then tens of thousands. This central object, hot, dense, glowing in infrared light, surrounded by a swirling disk of gas and dust, is called a protostar. It is not yet a star in the full sense. Nuclear fusion has not yet ignited within it. It is still gathering mass, still growing, still collapsing under gravity. But it is warm enough to glow, and in that warmth, there is already the suggestion of the fire to come. Protostars were not directly observed until the latter half of the 20th century, when infrared astronomy developed sufficiently to peer through the dust clouds that obscure them at visible wavelengths. The infrared astronomical satellite, launched in 1983, gave astronomers their first comprehensive survey of star-forming regions in infrared light, revealing protostars embedded in clouds that were entirely invisible to optical telescopes. What had once been darkness turned out to be full of infant suns. The disk of gas and dust that surrounds a forming protostar, called a protoplanetary disk, or proplyd, is not merely a byproduct of the star formation process. It is the raw material from which planets will eventually form. The same dust grains that were once drifting through the interstellar medium begin to collide and stick together. Tiny grains become pebbles, pebbles become boulders, boulders become planetesimals, and planetesimals slowly aggregate into the embryos of worlds. Star and planets form together, out of the same cloud, in the same long slow process, a realization that took centuries of careful observation and theory to fully appreciate. One of the most revealing moments in our understanding of this process came in the 1990s, when the Hubble Space Telescope captured images of the Orion Nebula in stunning detail and found it peppered with protoplanetary disks. Some of these disks were being eroded by the intense ultraviolet radiation from nearby massive young stars, their outer edges glowing brilliantly as the gas evaporated, a process called photoevaporation. Those disks might never complete the formation of planets before being stripped away. It was a sobering reminder that the universe does not guarantee the birth of worlds alongside every star. But for our own solar system, 4.5 billion years ago, the process ran to completion. A modest cloud of gas and dust in one of the outer arms of the Milky Way collapsed. It fragmented. And one particular fragment, one that happened to receive a shock-wave boost, perhaps from the explosion of a nearby massive star, began the slow, spinning, heated collapse that would eventually become the Sun and its family of 8 planets. We are the children of that collapse. We are the inheritors of that ancient disturbance in a forgotten cloud. And on quiet nights like this one, when the sky is clear and you can look up and see the Milky Way arching overhead, a pale river of light, softly luminous, you are looking at the place where that story began. Part 3, Ignition, the birth of a star and the main sequence. There is a moment, precise, irreversible, magnificent, when a collapsing protostar stops being merely a hot, dense cloud of gas and becomes a star. That moment is the ignition of nuclear fusion. For this to happen, the core of the protostar must reach an extraordinary temperature. At lower temperatures, the positively charged nuclei of hydrogen atoms repel each other with tremendous force, the electromagnetic repulsion between like charges. To push 2 protons close enough together for the strong nuclear force to take over and bind them, you need temperatures of approximately 10 million Kelvin. At such temperatures, the thermal energy of the particles is enough to overcome that electromagnetic barrier, at least for a fraction of the collisions taking place every second. When that threshold is crossed, hydrogen nuclei begin to fuse into helium, and with each fusion event, a small amount of mass is converted into an enormous amount of energy, according to Einstein's famous equation relating mass and energy through the square of the speed of light. The energy released floods outward as gamma rays and X-rays, which are absorbed and re-emitted countless times as they fight their way through the dense layers of the star above the core. By the time that energy emerges from the surface of the star as visible light and infrared radiation, it has taken tens of thousands of years to make the journey from the core to the surface, a journey measured in inches at a time, bouncing from particle to particle in the dense stellar interior, never traveling very far in any one direction before being absorbed and re-emitted again. The energy released by fusion creates the outward pressure that counteracts the inward pull of gravity. This is the fundamental balance that defines a star's life: gravity pulling inward, radiation pressure pushing outward. A star is, at its heart, a perpetual negotiation between these two forces. As long as the fuel lasts, the star maintains its size and temperature with remarkable consistency. This period of stable hydrogen burning is called the main sequence, and it is where a star spends the vast majority of its life. The main sequence is not a place in space. It is a category, a region on the diagram that Danish astronomer Edgar Hertzsprung and American astronomer Henry Norris Russell independently developed in the early 20th century, the Hertzsprung-Russell diagram, which plots a star's luminosity against its temperature or color. When astronomers first began systematically plotting stars on this diagram, something remarkable emerged. Most stars did not scatter randomly across the graph. They clustered along a diagonal band running from hot, brilliant, blue-white stars in the upper left to cool, dim, red stars in the lower right. This band is the main sequence, and it represents the fundamental organizing principle of stellar physics. The position a star occupies on the main sequence is determined almost entirely by one thing: its mass. More massive stars are hotter, brighter, and bluer. Less massive stars are cooler, dimmer, and redder. This relationship arises from the physics of the fusion rate. A more massive star must burn its fuel faster to maintain the pressure needed to support its greater weight. As a result, massive stars live dramatically shorter lives despite having more fuel to begin with. A star 10 times the mass of our Sun burns roughly 10,000 times as brightly and lives for only a few tens of millions of years. Our own Sun, a perfectly ordinary, middle-of-the-road yellow dwarf star of spectral type G2V, will spend approximately 10 billion years on the main sequence, and it is currently about halfway through that journey. The classification of stars was itself a human story of remarkable depth and determination. In the late 19th century, astronomers at the Harvard College Observatory undertook the enormous project of classifying the spectra of hundreds of thousands of stars, identifying the dark absorption lines in each star's light that correspond to specific elements absorbing specific wavelengths. The work was carried out largely by a team of women known informally as the Harvard Computers, among them Annie Jump Cannon, whose personal classification of over 350,000 stars established the system still in use today. Cannon could classify stars at the rate of 3 per minute simply by looking at their spectra, a skill developed through years of patient, meticulous work that was not initially recognized with the academic titles her male colleagues received as a matter of course. It was another of the Harvard computers, Cecilia Payne-Gaposchkin, who in 1925 made the discovery that stars are composed overwhelmingly of hydrogen, a result that was initially dismissed as impossible by the senior astronomer who reviewed her doctoral thesis, Henry Norris Russell himself. The conventional wisdom of the time held that stars must have a composition similar to Earth, with heavy elements dominant. Payne-Gaposchkin's analysis showed this was wrong. Stars are, by mass, about 74% hydrogen and about 24% helium, with all other elements making up only the remaining 2%. Russell eventually came to the same conclusion independently, published it, credited Payne-Gaposchkin, and the discovery was properly recognized, though the delay in recognition of her work remains a cautionary tale about how bias can slow the progress of science. The main sequence itself is a remarkably diverse population. At one extreme, the most massive stars, the O-type and B-type giants, blaze with the luminosity of 1,000,000 suns or more. The star Eta Carini, roughly 7,500 light-years away in the southern constellation Carina, is one of the most massive and luminous stars known, with an estimated mass somewhere between 100 and 200 times that of the Sun and a luminosity that may reach 5,000,000 times the solar value. It is a star so extreme that it barely contains itself. It has already thrown off enormous shells of gas in violent eruptions, and astronomers watch it closely, suspecting that it may eventually become one of the most spectacular stellar explosions in recent galactic history. At the other extreme, the faintest main sequence stars, the red dwarfs, or M-type stars, are so dim and cool that none of them is visible to the naked eye, despite the fact that they are the most common type of star in the galaxy, comprising perhaps 75% of all stars in the Milky Way. These stars are misers of energy, burning their hydrogen so slowly that many of them will remain on the main sequence for trillions of years, far longer than the current age of the universe. The universe has not yet been in existence long enough for even the first generation of red dwarf stars to have aged off the main sequence. They are the patient, enduring majority of the stellar population. Our Sun, humming along at the center of our solar system, converting 600 million tons of hydrogen into helium every second in its core, a process that simultaneously converts about 4 million tons of mass into pure energy each second, will continue this work for another 5 billion years or so before the hydrogen in its core is exhausted. 5 billion years is a span of time so large it resists comprehension. The entirety of the fossil record on Earth spans only about 600 million years. 5 billion years is more than 8 times that. By the time our Sun begins to change, whatever life inhabits Earth, if anything does, will be as different from us as we are from the first single-celled organisms that appeared in the ancient seas. But the main sequence is not the end of the story. It is only the middle. Part 4, The Long Middle, Stellar Structure and the Physics of Fusion. A star in the middle of its main sequence life appears, from the outside, to be a place of breathtaking calm. The surface shimmers. Light pours outward. The star rotates, gently or briskly depending on its age and mass. Sunspots, darker, cooler regions where powerful magnetic fields suppress the flow of heat from below, drift across the photosphere and fade. Solar flares and coronal mass ejections fling loops of plasma into space. But fundamentally, the star is in a state of dynamic equilibrium. It changes slowly, if at all, over millions or billions of years. Inside, however, the story is far less serene. The interior of a star like our Sun can be divided into several distinct layers, each with its own physics, its own character, its own role in the stellar drama. At the very center is the core, a region roughly a quarter of the Sun's radius, compressed to densities roughly 150 times that of liquid water, and heated to temperatures of 15 million Kelvin. This is where all the fusion takes place. This is the engine of the star. The fusion process in solar mass stars is called the proton-proton chain. It proceeds in several steps. 2 protons fuse to form a deuterium nucleus, releasing a positron and a neutrino in the process. The deuterium then fuses with another proton to form helium-3. 2 helium-3 nuclei then combine to form helium-4, releasing 2 protons back into the mix. The net result of this chain is that 4 hydrogen nuclei have become 1 helium nucleus, and approximately 0.7% of the initial mass has been converted into energy, specifically, into the kinetic energy of the particles produced and into the gamma rays that flood outward from the reaction zone. Those gamma rays do not travel far before being absorbed. The core of a star is so dense that a photon of light might travel only a centimeter or less before being absorbed by an ion and re-emitted in a random direction. The region surrounding the core, called the radiative zone, because energy is transported through it primarily by radiation, is so opaque that a photon's journey from core to surface can take between 10,000 and 170,000 years. Depending on estimates, as it bounces around in what physicists call a random walk. The same photon of light that leaves the Sun's surface today may have been born as a gamma ray in a nuclear reaction that took place while our earliest human ancestors were first learning to shape stone tools. Above the radiative zone lies the convection zone, where the temperature gradient becomes steep enough that radiation alone cannot efficiently transport the energy outward. Instead, great columns of hot gas rise toward the surface, cool, and sink back down again, a churning, turbulent circulation that brings the energy to the photosphere far more efficiently than radiation alone could manage. The surface expression of this convection is visible as the granulation of the solar surface, a pattern of bright, slightly raised granules surrounded by darker, slightly cooler lanes, each granule roughly 1,000 kilometers across, rising and falling over timescales of about 10 minutes. Look at the Sun through a solar telescope and the surface appears to be covered in a slowly churning, golden rice pudding, beautiful and restless and endlessly mobile. Above the photosphere, the visible surface of the Sun, lies the atmosphere. First the thin chromosphere, visible as a reddish rim during solar eclipses, where temperatures rise from the roughly 5,500 Kelvin of the photosphere to tens of thousands of Kelvin. And then the corona, the Sun's outer atmosphere, stretching millions of kilometers into space, its temperature mysteriously reaching 1 to 3 million Kelvin, 100 times hotter than the surface far below it. The reason for the corona's extraordinary temperature has puzzled solar physicists for decades. Why should the atmosphere get hotter as you move farther from the heat source? The answer appears to involve the complex magnetic field of the Sun, which threads through the corona and transfers energy through a combination of small-scale reconnection events, magnetic field lines snapping and reconnecting, releasing bursts of energy, and the propagation of magnetohydrodynamic waves called Alfvén waves. But the precise mechanism, and the relative importance of these different processes, remains an active area of research. In more massive stars, the fusion process operates through a different pathway, the carbon-nitrogen-oxygen cycle, or CNO cycle, in which carbon, nitrogen, and oxygen act as catalysts for the conversion of hydrogen to helium. The CNO cycle is more sensitive to temperature than the proton-proton chain, and it dominates in stars significantly more massive than the Sun. The internal structure of massive stars also differs. They tend to have convective cores and radiative envelopes, rather than the radiative cores and convective envelopes of lower-mass stars like the Sun. These structural differences have profound implications for how the stars evolve as they age. And age they do. Even in the long, slow middle of a star's life, change is happening. The helium ash produced by hydrogen fusion accumulates in the core, gradually increasing the core's mean molecular weight. This forces the core to contract slightly and heat up, which in turn causes the hydrogen-burning shell just above the core to burn faster. The star's luminosity increases slowly over its main sequence lifetime. Our own Sun is believed to be roughly 30% brighter today than it was when it first formed 4.5 billion years ago, a fact that poses the interesting puzzle of the faint young sun paradox. If the early Sun was so much dimmer, how did early Earth maintain temperatures warm enough for liquid water and life? The answer likely involves a thicker greenhouse gas atmosphere and other feedback mechanisms, but it remains an area of active discussion among planetary scientists and astrobiologists. The physics of stellar interiors became testable, rather than merely theoretical, with the development of helioseismology, the study of the Sun's oscillations. The Sun, like a vast bell, rings in thousands of different modes of vibration simultaneously, its surface rising and falling by tiny amounts as acoustic waves resonate through its interior. By carefully measuring these oscillations using instruments like those on the SOHO spacecraft, launched in 1995 and still operating today, scientists can probe the interior of the Sun in much the way geologists use seismic waves from earthquakes to study Earth's interior. The technique has revealed the rotation rate of different layers within the Sun, confirmed the depth and structure of the convection zone, and provided exquisitely detailed information about the temperature and density profiles within the solar interior. For decades, neutrino detectors measured only about 1/3 of the neutrinos predicted by solar models, a discrepancy known as the solar neutrino problem. The resolution of this problem turned out to require not a revision of solar physics but a revision of particle physics. Neutrinos, contrary to earlier assumptions, have mass, and they oscillate between different types, or flavors, as they travel. The electron neutrinos produced in the solar core were transforming into muon and tau neutrinos during their journey to Earth, and the early detectors were sensitive only to electron neutrinos. The discovery of neutrino oscillations, confirmed in the late 1990s and early 2000s, earned Takaaki Kajita and Arthur MacDonald the Nobel Prize in Physics in 2015, and it solved the solar neutrino problem by enriching our understanding of the quantum nature of these ghostly particles. Part 5: The Turning Point, when a star leaves the main sequence. Every equilibrium eventually ends. For a star, the end of the main sequence comes when the hydrogen in its core is exhausted, when the fraction of helium has grown so large that there is no longer enough hydrogen left to sustain the fusion reactions that have kept the core hot and the outward radiation pressure in balance with gravity. When this happens, the core begins to contract. There is no longer sufficient energy production to hold back the weight of the star above. Gravity, patient as ever, tightens its grip. The core shrinks. As it does, it heats up once more, gravitational energy converting to thermal energy. And this heat diffuses outward into the hydrogen layers just above the core, which now reach the temperature threshold for fusion. A shell of hydrogen ignites around the inert helium core. This hydrogen shell burning releases more energy than the core was producing before, and the excess energy drives an expansion of the outer layers of the star. The star begins to swell. Its surface expands outward, cooling as it does so, shifting in color from the yellow-white of its main sequence life toward orange and then red. The star has become, or is becoming, a red giant. The transformation to red giant is one of the most dramatic events in a star's life, though it occurs on timescales measured in millions of years. For a star like our Sun, the red giant phase will arrive in roughly 5 billion years. The Sun's photosphere will expand to roughly 100 times its current diameter. Mercury and Venus will almost certainly be engulfed. Whether Earth itself will be swallowed is a matter of active scientific debate. The Sun will lose significant mass during its giant phase, through intensified stellar winds, and as it loses mass its gravitational grip on Earth will relax, allowing Earth's orbit to expand. Some models suggest Earth will just barely escape. Others suggest it will spiral inward. Either way, Earth's surface will be sterilized long before the Sun's outer layers reach it, as the luminosity increases to the point where the oceans boil and the atmosphere is stripped away. The red giant phase is not a single, smooth transition but a complex series of events. While the core is contracting and the outer layers are expanding, something interesting is happening in the helium ash at the center. The core is becoming denser, hotter, more extreme. When the temperature in the core reaches approximately 100 million Kelvin, roughly 7 times the temperature required for hydrogen fusion, a new threshold is crossed. Helium nuclei begin to fuse together. The fusion of helium proceeds through a remarkable and delicate pathway called the triple alpha process. In the first step, 2 helium-4 nuclei, called alpha particles by early nuclear physicists, fuse to form beryllium-8. But beryllium-8 is extraordinarily unstable. It exists for only about 10 to the minus 17 seconds before decaying back into 2 alpha particles. For any helium to be converted into heavier elements, a third alpha particle must arrive and fuse with the beryllium-8 before it decays, a process so unlikely that early calculations suggested it could never happen at a significant rate. Then the British astronomer Fred Hoyle made one of the most remarkable theoretical predictions in the history of astrophysics. In the early 1950s, Hoyle argued that the triple alpha process must work, because carbon exists in the universe, and without the triple alpha process, there would be no way to produce it. For the process to work at the required rate, carbon-12 must have an excited nuclear energy state, a resonance, at precisely the right energy level to facilitate the reaction. Without such a resonance, the carbon nucleus produced would immediately redecay. Hoyle predicted its existence on purely astrophysical grounds, and then contacted nuclear physicist William Fowler at Caltech and asked him to look for it experimentally. Fowler found it. Carbon-12 does indeed have an excited state at almost exactly the energy Hoyle predicted. This resonance, now called the Hoyle state, is one of the most striking examples of what physicists sometimes call anthropic reasoning. Hoyle deduced a property of nuclear physics from the fact of our existence. If that resonance did not exist at precisely the right energy, the triple alpha process would be far less efficient, very little carbon would be produced in stars, and carbon-based life would likely not exist. William Fowler received the Nobel Prize in Physics in 1983 for his work on stellar nucleosynthesis, the process by which stars create elements. Fred Hoyle, extraordinarily, did not share the prize, a decision widely regarded as one of the Nobel Committee's great oversights. Hoyle had done more than anyone to establish the theoretical framework of nucleosynthesis, and his omission from the prize, attributed variously to his combative personality, his unconventional later theories, and the politics of the Nobel selection process, remains a source of controversy among physicists and historians of science. The helium flash releases as much energy as a small galaxy for those brief moments. But remarkably, none of this energy reaches the surface of the star. It is all absorbed in expanding the core and redistributing the energy through the stellar interior. From the outside, the helium flash is invisible. The star simply adjusts, its outer layers actually contracting somewhat as the core expands, the surface temperature rising slightly. The star settles into a new phase of stability, burning helium in its core alongside hydrogen in a shell, occupying a region of the Hertzsprung-Russell diagram called the horizontal branch. Part 6. The Giant Years, Red Giants, Asymptotic Giant Branch Stars, and Stellar Winds. The giant years of a star's life are among its most spectacular and most generous. Once a star has settled into helium core burning, it enters what astronomers call the horizontal branch, a phase of relative stability that lasts for roughly 100 million years in a solar mass star. The star is luminous and large, its reddish-orange light streaming out across the galaxy. It has joined the vast company of red giant stars visible in any direction you look on a clear night. Arcturus, the brightest star in the northern sky and the fourth brightest in the entire sky, is a red giant, a star about 1.5 times the Sun's mass that has expanded to about 25 times the Sun's radius. Aldebaran, the reddish eye of the bull in the constellation Taurus, is another, roughly 40 times the Sun's radius. These stars are not in their final decline. They are, by stellar standards, in a rich and active middle age. But helium does not burn forever either. As helium fuses to carbon and oxygen in the core, the helium is consumed and the core again accumulates an ash, this time, a core of carbon and oxygen. The helium shell just above this core continues to burn, and eventually a second hydrogen-burning shell adds its contribution above the helium shell. The star enters what astronomers call the asymptotic giant branch, a phase of repeated thermal pulses in which the helium shell periodically ignites and quenches, driving waves of expansion and contraction through the outer layers of the star. These thermal pulses, sometimes called helium shell flashes, have a profound effect on the composition of the star's outer layers. Each pulse drives a deep mixing event called a third dredge-up, in which material from the interior, freshly synthesized carbon and other elements, including the heavy elements produced by a process called the slow neutron capture process, or S process, is stirred up into the convective envelope and eventually mixed to the surface. Stars on the asymptotic giant branch can literally change their surface chemical composition over time as these dredge-up events enrich them with newly synthesized material. The S process is itself a remarkable story of elemental creation. In the interior of an asymptotic giant branch star, free neutrons, produced by specific nuclear reactions during the thermal pulses, can be captured by existing nuclei. Because the neutron flux is relatively slow compared to the time it takes for an unstable nucleus to decay, each newly created isotope has time to undergo radioactive decay before capturing another neutron, building up the heavier elements step by step, rung by rung up the ladder of the periodic table. Elements like strontium, barium, zirconium, and lead, and many of the lanthanide elements, are produced predominantly by the S process in asymptotic giant branch stars. Every barium atom in your body, every strontium atom in your bones, was forged in the slow, pulsing interior of a red giant star that died billions of years before the Sun was born. As the asymptotic giant branch star pulses and brightens, its outer layers are lifted by radiation pressure and driven away from the star in a strong stellar wind. This is not the modest wind of our own Sun, which steadily streams 1 million tons of particles per second into space. An asymptotic giant branch star can lose the equivalent of the Sun's entire mass to its wind in only 1,000,000 years or so, a rate that strips away the outer envelope of the star entirely within a few million years on the asymptotic giant branch. The material shed by the stellar wind does not simply disperse into the interstellar medium and vanish. It accumulates around the star in an expanding shell of gas and dust, a circumstellar envelope that can become enormously thick, absorbing almost all the star's visible light and re-radiating it as infrared emission. Stars in this heavily dust-enshrouded phase are called OH/IR stars, named for the hydroxyl and water masers detected in their circumstellar envelopes, and they are among the brightest sources of infrared radiation in the galaxy. Within the circumstellar envelopes of these dying giant stars, interstellar chemistry of remarkable richness takes place. The densities and temperatures at the boundary between the stellar atmosphere and the expanding wind are ideal for the formation of molecules and dust grains. Carbon-rich stars produce carbon dust, graphite grains and polycyclic aromatic hydrocarbons, while oxygen-rich stars produce silicate dust. These grains are the seeds of future solar systems. The dust that fills the interstellar medium, the dust that flows into molecular clouds and eventually into protoplanetary disks around young stars, a significant fraction of it originated in the winds of asymptotic giant branch stars. The solar system itself incorporated dust from many previous stellar generations, and some of that pre-solar dust has been identified in primitive meteorites on Earth, tiny grains that formed around other stars billions of years before the Sun was born, survived the formation of the solar system, and were ultimately incorporated into meteorites that fell to Earth and were collected and analyzed in laboratories. These pre-solar grains are identified by their anomalous isotopic compositions, ratios of isotopes that could not have been produced in the solar system and must therefore reflect the specific nucleosynthetic signature of the stars in which they formed. They are, in the truest sense, stardust, bits of other suns preserved in the rock of our solar system, tiny archives of the stellar history that preceded our own sun's birth. The stellar wind of an asymptotic giant branch star eventually blows away the outer hydrogen envelope entirely, leaving behind the hot, compressed remnant of the star's former core, a small, dense, extremely hot object surrounded by the shell of gas it has shed. As this central object heats up, reaching temperatures of tens of thousands, then 100,000, and eventually 200,000 Kelvin, its ultraviolet radiation floods the surrounding gas shell and ionizes it, causing it to glow in the gorgeous, intricate patterns that we observe as planetary nebulae. The name planetary nebula is a historical accident. William Herschel, who catalogued many of them in the late 18th century, noted that some of them appeared disc-like through his telescope, superficially resembling the discs of Uranus and Neptune he had discovered. The name stuck, even though planetary nebulae have nothing to do with planets. They are among the most photogenic objects in the universe: the Ring Nebula in Lyra, the Cat's Eye Nebula in Draco, the Helix Nebula in Aquarius, each one a unique sculpture of illuminated gas, shaped by the geometry of the stellar winds, the rotation of the dying star, the influence of any binary companions, and the complex hydrodynamics of the ejected material. The Helix Nebula, sometimes called the Eye of God in popular culture, lies approximately 650 light-years away, close enough to be studied in extraordinary detail. Hubble Space Telescope images reveal that the expanding shell is not a smooth ring but a complex structure of radial filaments and cometary knots, small, dense clumps of gas with tails pointing away from the central star, each one roughly the size of our solar system. Thousands of these knots populate the inner rim of the nebula, each one a tiny potential nursery of future matter, though the knots themselves will be dispersed long before any star formation could occur within them. Part 7: White Dwarfs, the quiet afterlife of sun-like stars. When the planetary nebula has expanded and thinned and eventually faded into the background of the galaxy, what remains at the center is one of the most extraordinary objects in the universe, a white dwarf. A white dwarf is what is left of a star after it has exhausted its nuclear fuel and shed its outer layers. For stars of up to roughly 8 times the Sun's mass, the vast majority of stars in the galaxy, the endpoint of stellar evolution is a white dwarf. For our Sun, this fate awaits in approximately 8 billion years. After its red giant and asymptotic giant branch phases, after it has puffed away its outer layers as a planetary nebula, the Sun's core will be left behind, a roughly Earth-sized sphere containing roughly half the Sun's original mass, compressed to an average density of approximately 1 million times that of water. A teaspoon of white dwarf material would weigh roughly 5 tons on Earth. No black dwarfs exist yet. The universe is not old enough. The oldest white dwarfs are still cooling, still faintly glowing. The coolest ones detected to date have surface temperatures of only a few thousand Kelvin, red and dim, and by dating their temperature against the cooling curves, astronomers can estimate the age of the stellar populations that produced them. The coolest white dwarfs in globular clusters provide one of the most reliable independent estimates of those clusters' ages, and through them, a constraint on the minimum age of the universe itself. When Chandrasekhar presented this result to the Royal Astronomical Society in 1935, it was publicly dismissed by the most eminent British astrophysicist of the day, Arthur Eddington, who declared that there must be a natural law preventing stars from behaving in so absurd a fashion as Chandrasekhar's calculations implied, that a star might collapse beyond the white dwarf stage into something even denser and stranger. Eddington used his enormous prestige to ridicule Chandrasekhar's work, and the younger scientist, devastated and disillusioned, shifted his research to other topics. It was not until 1983, nearly 50 years later, that Chandrasekhar received the Nobel Prize in Physics for his work on stellar structure and evolution, including the theoretical treatment that led to the discovery of the mass limit that now bears his name. In the meantime, the astrophysical community had come to understand that Eddington was wrong and Chandrasekhar was right, that stars can indeed collapse beyond the white dwarf stage, and that the results of such collapse are among the most extraordinary phenomena in the universe. But we will come to those in due time. White dwarfs, despite their apparent passivity, can be the sites of dramatic events when they are members of binary star systems, and a significant fraction of stars are in binary or multiple systems. If a white dwarf has a companion star that is close enough, it can accrete, pull, material from the companion, particularly when the companion expands to become a red giant and its outer layers overflow the gravitational boundary between the two stars, a surface called the Roche lobe. This transferred material accumulates on the surface of the white dwarf, forming a thin layer that gradually grows in density and temperature. When the accumulated hydrogen layer reaches a critical temperature and density, roughly 10 million Kelvin, it ignites explosively in a runaway fusion reaction. This event, visible from Earth as a sudden brightening of a star that was previously invisible to the naked eye, is called a nova, from the Latin for new star, because early observers believed they were witnessing the birth of a new star rather than a violent eruption on an existing one. A nova can brighten by a factor of 50,000 to 100,000 in a matter of days, becoming briefly visible in the daytime sky in the most extreme cases, before slowly fading over weeks and months as the ejected material disperses. The white dwarf itself survives the nova explosion and can repeat the process, accumulating another layer of hydrogen over thousands of years and erupting again. But if the white dwarf grows sufficiently close to the Chandrasekhar limit, either through repeated nova accretion or through the merging of two white dwarfs in a binary system, a far more catastrophic event becomes possible. This is the Type Ia supernova, one of the most powerful, and most cosmologically important, explosions in the universe. We will encounter Type Ia supernovae again when we discuss the most violent stellar deaths. But for now, let us hold the white dwarf in our minds as what it most commonly is, a quiet, cooling ember, the dignified residue of a life spent burning, a star that has given away everything it had and now simply rests and cools in the dark. Part 8, Massive Stars, Burning Through the Periodic Table. Not all stars end quietly. For stars significantly more massive than the Sun, stars of 8, 10, 20, 50 solar masses or more, the evolutionary story is far more violent, far more brief, and far more consequential for the universe around them. A massive star burns hydrogen on the main sequence with ferocious energy, illuminating its surroundings brilliantly and eroding the gas clouds around it with intense ultraviolet radiation. Where a solar mass star might spend 10 billion years on the main sequence, a star of 20 solar masses exhausts its hydrogen in only about 8 million years. And when it does, it enters the giant phase, but it does not stop at helium burning. When helium fusion exhausts the helium in the core of a massive star, the core contracts and heats further. At temperatures of about 500 million Kelvin, carbon fusion begins, two carbon nuclei fusing to form neon, sodium, magnesium. When carbon is exhausted, neon fusion begins at about 1.5 billion Kelvin. Then oxygen burning at about 2 billion Kelvin. Then silicon burning at about 3 billion Kelvin, the final stage of nuclear fusion in a massive star. By this point, the interior of the massive star resembles an onion, concentric shells of different burning stages nested around a growing iron core at the center. The outermost shell is still burning hydrogen into helium. Below that, a helium-burning shell. Then carbon, neon, oxygen, silicon, each shell burning faster and faster as the nuclear reactions become less efficient and more temperature-sensitive. The silicon shell burns for only a week. The oxygen shell for a few months. The carbon shell for perhaps a few centuries. The helium shell for tens of thousands of years. While the outer layers of the star remain relatively calm, the star still looks, from the outside, like a supergiant with a surface temperature and luminosity appropriate to its mass. The interior is racing through its final transformations at an accelerating pace. And the iron core is growing. Every second, more iron ash accumulates at the center, adding to the core's mass. The core is supported by electron degeneracy pressure, like a white dwarf. But a white dwarf has had time to cool, to settle, to slowly reach equilibrium. The iron core of a massive star is hot, growing rapidly, and it has no nuclear reactions to slow its accumulation of mass. In roughly a day, an extraordinarily brief span of time by stellar standards, the iron core grows to the Chandrasekhar limit. And then the core collapses. What happens next occurs on timescales so short, and involves physics so extreme, that it is difficult to describe in terms of everyday experience. In less than a second, in about a quarter of a second, the iron core, which is roughly the size of Earth, collapses to a sphere about 12 kilometers across. The density reaches nuclear density, the density at which atomic nuclei are literally touching. The collapse is so fast that the outer layers of the star do not yet know it has happened. Light from the collapsing core would take milliseconds to reach the outer layers. The star, in its last moment, still appears to be a supergiant blazing in the galaxy. The collapse is stopped abruptly when nuclear density is reached. Matter cannot be compressed beyond nuclear density. The strong nuclear force and neutron degeneracy pressure resist further compression with extraordinary stiffness. The inner core bounces, sending a shockwave outward through the still infalling outer core. But the shockwave quickly stalls. It loses energy fighting through the dense infalling material and dissociating iron nuclei into protons and neutrons. For a brief moment, everything hangs in balance. What revives the shock and drives the explosion appears to be the neutrinos. In the collapsed core, the density is so high that even neutrinos, those nearly non-interacting particles, are briefly trapped. The core radiates an enormous quantity of neutrinos as protons capture electrons and are converted to neutrons. In roughly 10 seconds, the collapsed core releases about 3 times 10 to the 46 joules of energy as neutrinos, more energy than the Sun will radiate in its entire 10 billion year lifetime, released in 10 seconds. Even though neutrinos interact very weakly with matter, the density of the material just above the collapsed core is so high that a tiny fraction of the neutrino energy is deposited there, heating that material, driving convection, and ultimately re-energizing the shock. The shock breaks free, accelerates outward through the outer layers of the star, and arrives at the stellar surface roughly an hour or two after the core collapsed. The outer layers of the star are blasted away at roughly 10% of the speed of light. The star explodes as a core-collapse supernova. The first quantitative confirmation that core-collapse supernovae produce a burst of neutrinos came on February 23, 1987, when a blue supergiant star called Sanjalik-69°202 in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, roughly 160,000 light-years away, exploded as supernova 1987A. A few hours before the optical brightening was observed, 3 neutrino detectors around the world, the Kamiokande 2 detector in Japan, the IMB detector in Ohio, and the Baksan detector in Russia, registered a burst of neutrino events lasting about 12 seconds. 25 events in total across the 3 detectors, a tiny number compared to the 10 to the 58 neutrinos actually produced, but enough to confirm the basic picture of core collapse and to provide a wealth of information about the physics of the collapsed core. It was one of the most significant moments in observational astrophysics of the 20th century. Supernova 1987A was close enough to be visible to the naked eye in the southern hemisphere, the brightest supernova observed since Kepler's supernova in 1604. Astronomers around the world turned their telescopes toward it and watched as it brightened over weeks and then slowly faded, powered in its decline by the radioactive decay of nickel-56 into cobalt-56 and then into iron-56, decay chains whose rates matched precisely the observed light curve. The expanding shell of debris has been watched for decades since, revealing the complex structure of the ejecta, the rings of material blown off by the star in its pre-supernova winds, the shock wave plowing through the surrounding gas, and, perhaps most tantalizing of all, the expected but not yet conclusively detected presence at the center of the explosion of a neutron star. Part 9: Supernovae, the universe's great recycling events. A supernova is not simply a death. It is, perhaps more than any other event in the universe, an act of generosity on a cosmic scale. The violence of a supernova explosion is almost beyond reckoning. In the seconds and hours of the explosion, the expanding shock wave heats the infalling stellar material to temperatures sufficient to drive nucleosynthesis at a frantic rate. New elements are forged in the explosion itself, elements that could not be produced in the relatively sedate environment of stellar interiors. The rapid neutron capture process, or R process, occurs in the extreme neutron-rich environment of a core-collapse supernova, though recent observations suggest that the R process may occur even more efficiently in the mergers of two neutron stars. The R process builds elements heavier than iron extremely rapidly, pushing nuclei up through the periodic table by capturing neutrons faster than radioactive decay can occur. Gold, platinum, uranium, thorium, the heaviest naturally occurring elements, are products of the R process. The gold in your jewelry, the uranium in nuclear reactors, the thorium in certain lantern mantles, all of it was forged in the extreme environments of stellar death. The explosion itself ejects roughly 10 solar masses of material at velocities of thousands of kilometers per second. This material expands outward into the surrounding interstellar medium, sweeping up gas, driving shockwaves, heating and ionizing the surrounding region. The expanding bubble of hot, enriched gas, called a supernova remnant, can be traced for thousands of years after the explosion. The Crab Nebula in Taurus, which appears in optical telescopes as a tangled network of glowing filaments roughly 11 light-years across, is the remnant of a supernova observed by Chinese and Arab astronomers in the year 1054, nearly 1,000 years ago. It is still expanding today, at about 1,500 kilometers per second. At its center is a pulsar, a rapidly spinning neutron star whose powerful magnetic field sweeps beams of radiation around like a lighthouse, visible to us as a pulse 30 times per second. The Cassiopeia, a supernova remnant, roughly 11,000 light-years away and estimated to have exploded around 1680, though curiously, no reliable historical record of the event exists, despite it likely being bright enough to see with the naked eye at peak brightness, is one of the brightest radio sources in the sky outside the solar system. X-ray images from the Chandra X-ray Observatory reveal a roiling, turbulent structure of hot gas and ejecta, with clear chemical stratification visible, different elements distributed in different ways through the remnant, reflecting the onion layer structure of the original star and the dynamics of the explosion. At the center of Cassiopeia A neutron star only about 25 kilometers across but more massive than the Sun radiates X-rays, its surface still hot from the violence of its birth. Supernova remnants do more than preserve the record of the explosions that created them. They are essential drivers of the chemical and physical evolution of the interstellar medium. The heavy elements they distribute mix with the surrounding gas and are eventually incorporated into new molecular clouds, new protoplanetary disks, new solar systems. The shock waves they drive compress the interstellar medium, potentially triggering new episodes of star formation. The cosmic rays they accelerate, charged particles moving at near relativistic speeds, diffuse through the galaxy, contributing to the energy density of the interstellar medium and to the ionization of molecular clouds. Type Ia supernovae, the explosions of white dwarfs near the Chandrasekhar limit in binary systems, are a distinct class of supernova with a different and cosmologically enormous significance. Because the white dwarf always explodes at approximately the same mass and therefore approximately the same energy, Type Ia supernovae have roughly the same intrinsic luminosity everywhere in the universe. They are what astronomers call standard candles, objects whose true brightness is known, so that their apparent brightness tells you how far away they are. In the late 1990s, two teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team led by Brian Schmidt at the Australian National University and including Adam Rees at the Space Telescope Science Institute, were using Type Ia supernovae to measure the rate at which the expansion of the universe was decelerating. They expected to find deceleration, because gravity should be slowing the expansion over time. What they found instead was acceleration. The universe is not decelerating. It is speeding up in its expansion, driven by some form of energy inherent to space itself, which we call dark energy, and which contributes roughly 68% of the total energy content of the universe. The discovery of cosmic acceleration earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. It is arguably the most unexpected and consequential discovery in cosmology since the discovery of the expanding universe by Edwin Hubble in the 1920s. And it arose from the patient, careful observation of the light of dying stars in distant galaxies, from counting the fading embers of stellar catastrophes billions of light-years away, and noticing that they were slightly fainter, slightly more distant, than the standard cosmological models predicted. The universe itself, it turns out, revealed one of its deepest secrets through the deaths of stars. Part 10, Neutron Stars, the Strange and Spinning Dead. When a massive star explodes as a supernova, the outer layers are flung into space. But the core remains. And the core has been compressed, in the violence of the collapse, to an object unlike anything else in the known universe. A neutron star is born in the moment the iron core of a massive star collapses. As the density of the collapsing core reaches nuclear density, electrons and protons are forced together into neutrons by the extreme pressure. The result is an object composed almost entirely of neutrons, packed together at the density of an atomic nucleus, held in balance by neutron degeneracy pressure and the strong nuclear force itself. A neutron star is, in some sense, a single enormous atomic nucleus, or rather, a droplet of nuclear matter, roughly 10 to 13 kilometers in radius but containing between 1 and 2.5 solar masses of material. The densities involved are extraordinary. At the center of a neutron star, the density may reach several times nuclear density, a regime where our current understanding of the strong nuclear force is strained to its limits and the behavior of matter is genuinely uncertain. Several theoretical models of the neutron star interior have been proposed, involving everything from exotic phases of nuclear matter to the presence of hyperons, particles containing strange quarks, to the possible formation of quark matter, in which quarks roam freely rather than being confined within nuclei. Which of these descriptions is correct depends on the equation of state of extremely dense matter, a quantity that can be constrained, at least partially, by measuring the masses and radii of neutron stars. A freshly born neutron star inherits the angular momentum of its progenitor core, greatly amplified by the collapse, just as the figure skater spins faster when she pulls in her arms. A neutron star can spin hundreds of times per second at birth. It also inherits the magnetic field of the progenitor, amplified by the collapse of the field lines into a far smaller volume. The magnetic fields of neutron stars are among the most intense in the universe, typically around 10 to the 12 Gauss, roughly 1 trillion times the strength of Earth's magnetic field. This combination of rapid rotation and intense magnetic field means that a neutron star radiates electromagnetic beams from its magnetic poles, radio waves, X-rays, gamma rays, that sweep around with every rotation, like a cosmic lighthouse. When Earth happens to lie within the sweep of one of these beams, we detect a pulse of radiation with each rotation. Such a neutron star is called a pulsar. Pulsars were discovered by accident in 1967 by Jocelyn Bell Burnell and Anthony Hewish at the University of Cambridge, using a radio telescope that Bell Burnell, a graduate student at the time, had helped build. Bell Burnell noticed a peculiar signal in the data, pulses of radio emission arriving with extraordinary regularity, at an interval of 1.337 seconds. The signal was so precise, so perfectly timed, that it was initially unclear whether it could be natural. The Cambridge team briefly labeled it LGM-1, for Little Green Men, half joking, half seriously uncertain about its origin. Bell Burnell herself recalled being slightly annoyed by the signal, suspecting it was man-made interference, before the possibilities of its natural astrophysical origin became clear. Further analysis, and the discovery of additional pulsars, established that these were rotating neutron stars, the most precise natural clocks in the universe. Anthony Hewish shared the 1974 Nobel Prize in Physics for the discovery. Jocelyn Bell Burnell did not, despite having been the one to notice and identify the signal. The omission sparked significant debate about the Nobel Committee's treatment of students and junior researchers, and Bell Burnell, who went on to a distinguished career and received many other honors, handled the situation with extraordinary grace and generosity, continuing to advocate for inclusivity in science and eventually donating her £3 million Breakthrough Prize Award to fund physics studentships for women, underrepresented ethnic minorities, and refugee students. The most extreme pulsars, called millisecond pulsars, spin hundreds of times per second. They are old neutron stars that have been spun up by accreting matter from a binary companion star over millions of years, the infalling material adding angular momentum and increasing the spin rate. PSRJ 1748-2446 AD, discovered in 2005, spins at 716 revolutions per second, making its equator move at roughly 24% of the speed of light. The stability of millisecond pulsars as timekeepers rivals the best atomic clocks on Earth, making arrays of millisecond pulsars useful as a detector for low-frequency gravitational waves. The pulsar timing array experiments have been showing increasingly strong evidence for a gravitational wave background that likely has contributions from merging supermassive black holes in the distant universe. Some neutron stars have magnetic fields vastly stronger even than ordinary pulsars, objects called magnetars, with fields of 10 to the 15 Gauss or more. In magnetars, the magnetic field energy dominates the dynamics of the star, distorting its crust and driving violent flares and bursts of X-ray and gamma-ray emission. On December 27, 2004, a magnetar called SGR 1806-20, about 50,000 light-years away, released in a fraction of a second more energy than the Sun emits in 150,000 years. The burst was so intense that it partially ionized Earth's upper atmosphere, detectable as a disturbance in the ionosphere despite the source being 50,000 light-years away. It was the most energetic event ever recorded from beyond the solar system at that time, a reminder that the universe contains phenomena of staggering violence, most of which we observe only from a fortunate and safe distance. The interior structure of neutron stars may be the most exotic environment in the observable universe. Below the thin solid crust, a layer of neutron-rich nuclei in a crystalline lattice, only a kilometer or so thick, lies a region where neutrons flow without viscosity in a superfluid state. Deeper still, at densities approaching and exceeding nuclear saturation density, the behavior of matter becomes genuinely uncertain. Whether neutron stars harbor cores of quark-gluon plasma, the state of matter that existed in the very early universe, fractions of a second after the Big Bang, is a question that remains unanswered. Measuring the radii of neutron stars with sufficient precision to distinguish between different equations of state is one of the central challenges of modern neutron star astrophysics. The Neutron Star Interior Composition Explorer, NICER, is a NASA instrument installed on the International Space Station in 2017 and designed precisely to address this question. By timing X-ray pulses from rotating neutron stars with extraordinary precision and modeling the shape of the pulse, which is affected by the curvature of spacetime near the neutron star, itself depending on the star's compactness, NICER has been measuring neutron star radii to within a few percent. The results so far suggest that neutron stars of about 1.4 solar masses have radii of roughly 12 to 13 kilometers, constraints that rule out some of the more exotic theoretical models of the interior and favor equations of state in which the core remains hadronic rather than quark matter dominated, at least at these masses. Perhaps the most remarkable neutron star story of recent years, however, is not about isolated pulsars but about colliding ones. When two neutron stars orbit each other in a binary system, they radiate gravitational waves, ripples in the fabric of spacetime, predicted by Einstein in 1916, finally directly detected by the LIGO and Virgo gravitational wave detectors in 2015. As gravitational waves carry energy away from the binary system, the two stars spiral inward toward each other. Over millions of years, the orbit tightens. And eventually, in the brief, cataclysmic final minutes of their orbital dance, they merge. On August 17, 2017, the LIGO and Virgo detectors detected gravitational waves from the merger of two neutron stars for the first time, an event designated GW 170817 in the constellation Hydra, approximately 130 million light-years away. Within 2 seconds of the gravitational wave signal, the Fermi and integral gamma-ray satellites detected a short gamma-ray burst from the same direction. In the days and weeks that followed, telescopes across the electromagnetic spectrum tracked the fading glow of the merger, a kilonova, powered by the radioactive decay of freshly synthesized heavy elements. The spectroscopic analysis of the kilonova revealed the signatures of heavy R-process elements. Strontium was specifically identified, confirming that neutron star mergers are indeed a major site of heavy element production. For the first time in history, a single astronomical event had been observed simultaneously in gravitational waves and electromagnetic radiation, the dawn of what astronomers call multi-messenger astronomy. The information content of such observations is vastly richer than either type of observation alone. The gravitational wave signal tells us about the masses and spins of the merging stars, and through the cosmological redshift, provides an independent measurement of the Hubble constant, the rate of expansion of the universe, that does not depend on the cosmic distance ladder built from Cepheid variables and supernovae. The electromagnetic observations tell us about the ejecta composition, the energetics, and the nature of the remnant. Together, they are beginning to resolve questions that neither gravitational wave nor electromagnetic observations alone could answer. Part 11: Black Holes, where gravity wins completely. There is a threshold beyond which even neutron degeneracy pressure cannot hold back gravity. When the mass of the collapsed stellar core exceeds roughly 2 to 3 solar masses, the exact value depending on the still uncertain equation of state of dense matter, there is no known force in nature that can prevent continued collapse. The core does not stop at nuclear density. It does not become a neutron star. It collapses further and further, without limit. The result is a black hole. The concept of a region of space from which nothing, not even light, can escape was first proposed in a recognizably modern form by the English natural philosopher John Michell in 1783, who called them dark stars, and independently by the French mathematician Pierre-Simon Laplace in 1796. They had in mind the Newtonian picture of escape velocity, the speed at which an object must be thrown upward to escape a planet's gravity. For a sufficiently massive and compact object, the escape velocity exceeds the speed of light, and so even light cannot escape. The modern understanding of black holes, however, is rooted not in Newtonian mechanics but in Einstein's general theory of relativity, published in 1915. In general relativity, gravity is not a force in the Newtonian sense but a curvature of the four-dimensional fabric of spacetime, caused by the presence of mass and energy. A massive, compact object curves spacetime so severely that near its surface, all paths through spacetime, including the paths of light rays, curve inward. Beyond a certain boundary, the event horizon, even light moving outward is dragged back by the curvature. The event horizon is not a physical surface. It is a mathematical boundary, a point of no return in spacetime. The mathematical solution describing a black hole was first found by Carl Schwarzschild in 1916, just months after Einstein published his field equations, and while Schwarzschild was serving on the Eastern Front during World War I. He sent his solution to Einstein in a letter from the trenches, and Einstein presented it to the Prussian Academy of Sciences on Schwarzschild's behalf. Schwarzschild died a few months later from a disease contracted at the front, never knowing the profound significance his solution would have for our understanding of the universe. The radius of the event horizon of a black hole, the Schwarzschild radius, depends only on the mass. For a black hole of 1 solar mass, the Schwarzschild radius is about 3 kilometers. For a black hole of 10 solar masses, it is 30 kilometers. For the supermassive black holes found at the centers of galaxies, objects with masses of millions or billions of solar masses, the Schwarzschild radius can be millions of kilometers across, larger than the orbit of Mercury around the Sun. Black holes formed from the collapse of individual massive stars are called stellar mass black holes, and they typically have masses between a few and a few tens of solar masses. They are expected to form when stars heavier than roughly 25 to 30 solar masses explode, though the relationship between progenitor mass and outcome is not simple and depends on factors including the stellar rotation and metallicity. In some cases, the explosion may be weak or absent, and the star simply collapses silently into a black hole, a failed supernova. There is observational evidence for such events. Surveys of nearby galaxies have identified massive stars that disappeared without producing the expected supernova brightening, one candidate being a star in NGC 6946 that faded and disappeared between 2009 and 2015. Stellar mass black holes can be detected when they are members of binary systems with ordinary stars. Material from the companion star falls toward the black hole, forming an accretion disk, a swirling disk of hot gas spiraling inward toward the event horizon. The innermost regions of the accretion disk can reach temperatures of millions of Kelvin, radiating brilliantly in X-rays. The first stellar mass black hole to be conclusively identified was Cygnus X1, an intense X-ray source in the constellation Cygnus, whose compact object was shown through careful measurement of the orbital dynamics of its companion star to be too massive to be a neutron star, the first observational evidence for the existence of stellar mass black holes. Stephen Hawking famously made a bet in 1974 with his colleague Kip Thorne that Cygnus X1 was not a black hole. He conceded the bet in 1990. Black holes, despite their reputation as cosmic vacuum cleaners, are not in fact particularly voracious when simply sitting in space. An object orbiting at a safe distance from a black hole experiences gravity no differently than it would from any other mass of the same size. If the Sun were somehow instantly replaced by a black hole of the same mass, Earth would continue orbiting in exactly the same path it follows today. The black hole would be no more dangerous to Earth's orbit than the Sun is now. What makes black holes dangerous is their compactness, the fact that you can approach so much closer before the tidal forces become lethal. The tidal forces near a stellar mass black hole are indeed lethal in a dramatic fashion. An object falling toward a stellar mass black hole would experience extreme stretching in the direction of the hole and compression perpendicular to it, a process physicists call spaghettification, which is a word that sounds almost playful given the reality it describes. A human body crossing the event horizon of a stellar mass black hole would be stretched to a thread of atoms before reaching the event horizon itself. The experience near a supermassive black hole would be entirely different, because the tidal forces scale inversely with the square of the mass. The tidal forces at the event horizon of a billion solar mass black hole are actually quite mild. A person could, in principle, cross the event horizon of a supermassive black hole without immediately noticing anything unusual, though they would subsequently find it impossible to escape, and would experience the singularity, the point of infinite density at the center, within a finite and calculable amount of proper time. What happens at the singularity itself, at the mathematical center of the black hole where general relativity predicts infinite density and curvature, is one of the great open questions of theoretical physics. General relativity breaks down at the singularity, producing infinite values that signal the failure of the theory to correctly describe that regime. The resolution of this breakdown requires a theory of quantum gravity, a framework that successfully unites quantum mechanics with general relativity, which has been the deepest unsolved problem in theoretical physics for nearly a century. One of the most profound theoretical contributions to black hole physics came from Stephen Hawking in 1974, when he showed that black holes are not entirely black. Quantum mechanical effects near the event horizon caused black holes to emit thermal radiation, now called Hawking radiation, at a temperature inversely proportional to the mass of the black hole. For stellar mass black holes, the Hawking temperature is extraordinarily small, about 10 to the -7 Kelvin above absolute zero, utterly unmeasurable with any current technology, swamped by the 3 Kelvin cosmic microwave background radiation bathing the entire universe. But the theoretical implications are profound. Black holes are not eternal objects. Over unimaginably long timescales, they radiate away their mass and eventually evaporate, ending in a final burst of emission. For a solar mass black hole, the evaporation time is roughly 2 times 10 to the 74th years, a span so vast it makes the current age of the universe, at 14 billion years, seem like a brief opening note in a symphony of almost incomprehensible length. The existence of supermassive black holes at the centers of virtually all large galaxies, with masses of millions to tens of billions of solar masses, raises profound questions about how they formed and grew. They are too massive to have formed simply from the collapse of individual stars. They must have grown through a combination of mergers, where galaxies and their central black holes combine, and accretion, where vast quantities of gas fall into the central black hole over cosmic time. The most distant quasars, the brilliant nuclei of early galaxies powered by the accretion of matter onto supermassive black holes, have been observed at redshifts corresponding to times when the universe was less than 1 billion years old. The black holes powering these early quasars already had masses of 1 billion solar masses or more. How they grew so large so quickly is a major unsolved problem in cosmology. The first direct image of a black hole, or more precisely, of the shadow of a black hole against the glow of its surrounding accretion disk, was obtained by the Event Horizon Telescope collaboration in 2019. The image revealed the supermassive black hole at the center of the elliptical galaxy M87, 55 million light-years away, a fuzzy ring of orange light surrounding a dark central shadow. The black hole has a mass of about 6.5 billion solar masses, and its shadow, the region where gravity bends light so strongly that photons orbit and are captured, spans roughly 40 microarcseconds across, roughly equivalent to imaging an orange on the Moon. Achieving the resolution required to image this shadow required a virtual telescope the size of the entire Earth, constructed by linking radio observatories across multiple continents and coordinating their observations with extraordinary precision. In 2022, the Event Horizon Telescope collaboration published a second image, this time of Sagittarius A*, the supermassive black hole at the center of our own Milky Way, about 26,000 light-years away and about 4 million times the mass of the Sun. The image showed the same characteristic ring structure, a donut of glowing gas surrounding a darker shadow, and confirmed theoretical predictions about the shape and size of the shadow with remarkable accuracy. Seeing the heart of our own galaxy for the first time, frozen in the pixels of a radio image, was a moment of quiet, extraordinary significance. Part 12: The Cosmic Legacy, What Stellar Death Gives to the Universe. And so we arrive at the final chapter of this long, deep story. Not an ending, really, for the universe does not end, and the story of stars does not end. But a moment to gather what we have learned, to hold it gently, and to feel its weight and wonder. Every star that has ever burned and died has left something behind. Not just the white dwarf, the neutron star, the black hole, those dense, exotic remnants of the stellar body itself, but something far more expansive. Every star that has ever existed has contributed to the composition of the universe that follows it. Every star has enriched the interstellar medium with the products of its nuclear burning, seeded the galaxy with the raw materials for future generations of stars and planets and, in at least one case that we know of, life. The story of stellar nucleosynthesis, the process by which stars build the elements, was laid out in its most complete form in a landmark paper published in 1957 by 4 scientists, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. The paper, known by the initials of its authors as B superscript 2FH, described 8 distinct processes by which elements are synthesized in stars and stellar explosions, and provided the theoretical framework that explained, for the first time, why the universe has the chemical composition it does. It is one of the most important papers in the history of astrophysics, and its publication was a moment of extraordinary synthesis, bringing together nuclear physics, astrophysics, and observational astronomy into a coherent and beautiful story about where the elements come from. The answer that story gives is both simple and humbling. Hydrogen and most of the helium in the universe were produced in the Big Bang itself, in the first few minutes of cosmic history, when the temperature was high enough for proton-proton fusion. Everything heavier than helium, every carbon atom, every oxygen atom, every nitrogen atom, every silicon and iron and gold and uranium atom, was made inside stars, or in the violent events of stellar death, and distributed through the universe by stellar winds and supernova explosions over the course of billions of years of cosmic history. This means that you are, in a very literal and scientifically precise sense, made of stardust. The carbon in your DNA was forged in the triple alpha process in the core of a red giant star that died billions of years before the sun was born. The oxygen in your lungs was synthesized in the oxygen-burning shell of a massive star in its final centuries of life. The iron in your red blood cells was produced in the silicon-burning shell of a massive star just before it exploded, and was distributed through the galaxy by the supernova shockwave. The calcium in your bones came from supernovae. The nitrogen in your proteins came from a combination of stellar winds and explosions. The gold in any jewelry you wear was forged in the collision of neutron stars, or possibly in the R process during a core collapse supernova, and scattered through the interstellar medium across billions of years before finding its way into the molecular cloud that became the solar system. The Earth itself is a monument to stellar death. The rocky material of our planet, the silicates, the iron-nickel core, the diverse chemistry of the crust and mantle, all of it was assembled from the debris of previous stellar generations. Geologists studying the oldest minerals on Earth, tiny zircon crystals from the Jack Hills in Western Australia, some dating to 4.4 billion years ago, are examining material that was recycled from the pre-solar interstellar medium, itself a product of billions of years of stellar cycling before the Sun formed. The rock beneath your feet carries within it the memory of stars that burned and died before our solar system existed. The cycle of stellar birth and death is itself one of the great organizing processes of the universe. Stars form from molecular clouds. They burn for millions or billions of years. They die, returning their enriched material to the interstellar medium. That material is incorporated into new molecular clouds, which form new stars, but now with a richer chemical palette than the generation before. Each generation of stars makes the universe chemically more complex. Each generation creates the conditions for the next to go further. The first generation of stars, the population 3 stars, worked with almost pure hydrogen and helium. The second generation, the population 2 stars, ancient, metal-poor stars found today in globular clusters and the halo of the Milky Way, worked with small but growing amounts of heavier elements. The third generation, population 1 stars, including our Sun, formed from gas already enriched by billions of years of previous stellar processing, with enough heavy elements to form rocky planets, complex chemistry, and ultimately biology. We are the product of that long, slow chemical enrichment. We exist because enough generations of stars lived and died before our Sun was born to seed the galaxy with the complex chemistry of life. The carbon, oxygen, nitrogen, phosphorus, and sulfur that make up the molecules of biology, the building blocks of DNA, proteins, lipids, carbohydrates, all required the work of many stellar generations to produce in sufficient quantities. Life, as we know it, is not just dependent on stars for light and warmth. Life is dependent on stellar death for its very molecular existence. The astronomer Carl Sagan expressed this beautifully and simply when he said that we are a way for the cosmos to know itself. The atoms of our bodies, assembled by stellar processes over billions of years, have been arranged by the further processes of planetary formation, geochemistry, and biological evolution into beings capable of looking back at the stars and understanding something of how they work. The universe has not merely produced us. In producing us, it has produced a mechanism for its own self-examination. The curiosity that draws you to listen to a story about stars on a quiet night is itself a product of stellar evolution, as natural, and as cosmic, as the fusion of hydrogen in the core of the Sun. And what of the future? Our Sun has roughly 5 billion years remaining on the main sequence. In that time, the geological and biological history of Earth will continue to unfold, assuming it does not meet some earlier catastrophe, in ways we cannot begin to predict. Eventually, the Sun will leave the main sequence, swell into a red giant, shed its outer layers as a planetary nebula, and settle into its eternal life as a white dwarf. The outer planets of the solar system, Jupiter, Saturn, Uranus, Neptune, will survive the Sun's giant phase, their orbits expanding as the Sun loses mass, their surfaces briefly warmed by the increased luminosity before the central white dwarf cools and they are left in cold darkness. The Milky Way galaxy itself will not remain unchanged. In roughly 4.5 billion years, around the same time our Sun is beginning its red giant phase, the Milky Way will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor. The merger will not be a catastrophic collision of individual stars. The stars in both galaxies are too widely spaced for direct collisions to be common, but the gravitational disruption will be profound. New bursts of star formation will be triggered as gas clouds collide and compress. The elegant spiral arms of both galaxies will be distorted and eventually scrambled into a new, merged structure, an elliptical or lenticular galaxy, perhaps, the stellar populations of two great galaxies now tumbled together into a single vast stellar community. In the far future, in the cold, dark, slow age of the universe billions and trillions of years from now, the rate of star formation will decline as the gas supply of galaxies is gradually consumed. The long-lived red dwarf stars will continue burning patiently, but new star formation will become increasingly rare. Eventually, after perhaps 100 trillion years, the last stars will exhaust their hydrogen and die. White dwarfs will cool to black dwarfs. Neutron stars will slowly spin down. Black holes will begin their incomprehensibly slow evaporation by Hawking radiation. The universe will enter a dark, cold, quiet age of almost unimaginable duration, a far future epoch so remote that the current age of the universe is an insignificant fraction of its length. But that distant darkness does not diminish what has happened in the billions of years of stellar burning that have already occurred. In those years, the universe built complexity from simplicity. From the near-uniform hydrogen and helium of the Big Bang, it created, through the patient work of stellar gravity and nuclear fire and violent death, the entire richness of the periodic table. From that chemical richness, on at least one world, it created life. From that life, it created minds capable of wondering about their own origins. The life cycle of stars is, in the deepest sense, the story of how the universe produced the conditions for its own self-awareness. It is a story written in nuclear fire and gravitational collapse, in the slow spinning of neutron stars and the dark silence of black holes, in the glowing beauty of nebulae and the patient dimming of white dwarfs. It is a story that is still being written, in every molecular cloud where gravity is today pulling gas together toward new ignition, in every protoplanetary disk where dust grains are colliding and beginning the long journey toward a world, in every red giant shedding its outer layers into the beauty of a planetary nebula, in every neutron star quietly radiating its pulsed lighthouse beam across the darkness. You are part of this story. You have always been part of it. The atoms that make you up have cycled through stellar interiors and interstellar clouds and the chemistry of primordial oceans and the slow complexity of biological evolution. They have been part of stars, and they will be part of stars again, long after the specific pattern that is you has dispersed. Those atoms will continue their journey through the universe's endless recycling. And on quiet nights, when the stars are out and the world is still, something in us recognizes this connection. We look up and feel, even if we cannot articulate why, that we belong to what we see. We are not separate from the stars. We are their children. We carry their history in our bodies and their future in our hands. Tonight, as you drift toward sleep, carry that with you. You are made of the universe looking at itself. You are the legacy of a billion stellar generations. And the atoms of your body, quietly maintaining the chemistry of your rest, have been on a journey of 4 billion years to arrive at this moment, in this darkness, in this gentle drift toward dream. Closing meditation. The stars are still out there. Beyond the ceiling above you, beyond the atmosphere of this small and precious planet, the Milky Way arches through the darkness, 200 billion stars, each one a sun, each one a story of ignition and burning and eventual transformation. Some of them are young, blazing blue-white, still wrapped in the remnants of the clouds that birthed them. Some of them are ancient and red, nearing the end of their long, slow lives. Some of them have already died and been reborn as white dwarfs and neutron stars and black holes, continuing their existence in forms utterly different from what they were before. And somewhere in the body of the Milky Way, roughly halfway out from the center, along the inner edge of the Orion Arm, a modest yellow star burns steadily. It has been burning for 4.5 billion years. It will burn for 5 billion more. Around it, 8 planets move in their ancient orbits. On the third planet, thin and precious, a layer of atmosphere holds the warmth of that star close to a blue and green surface. On that surface, you rest. You breathe slowly. In and out. The oxygen filling your lungs was made in the burning shell of a star that died before the sun was born. The iron in your blood carries it through your body, iron that was forged in the final hours of a massive star's life and scattered by a supernova explosion billions of years ago. You are the universe, resting, breathing, dreaming. Let your thoughts grow quiet now. Let the images of nebulae and supernovae and neutron stars gently fade, like light from a distant star reaching the edge of visibility. You have traveled far tonight. You have visited the birth of the cosmos, the ignition of the first stars, the long patient burning of stellar lives, and the spectacular deaths that seeded the universe with everything it needed to make you. Now rest. Let the story continue without your watching. It will be there when you wake, the stars still burning, the universe still expanding, the great cycle of matter and energy still turning, patient and vast and beautiful, as it has always been and as it will continue to be. Sleep now. If you're still awake, the universe is vast and full of wonder. Subscribe to Cosmos and Dreams for a new discovery every week. Sweet dreams.